Look at the calm waters of Lake Bunyoni. The surface acts as a perfect mathematical mirror, creating an exact upside-down copy of the hills above. We rely on this exact mathematical balance in human trades, too. When a tailor cuts a dress, they fold the fabric perfectly in half before making a single cut, ensuring the sides match exactly. In geometry, that central fold is called the line of symmetry, or mirror line. If you place an ink drop on one side of folded paper and press it closed, the crease acts as the mirror, leaving a symmetrical shape when opened. It's a common misconception that all standard shapes fold symmetrically in every direction. If you fold a rectangle along its diagonal line, the corners will not meet. A standard rectangle only has 2 lines of symmetry, not 4. When reflecting, 3 rules apply. First, the image is congruent, the size never changes. Second, it is laterally inverted, or flipped left to right. And third, every point on the image is the exact same distance from the mirror line as the original object. Understanding these 3 physical rules allows us to calculate exact geometric reflections in abstract mathematics. Here is a Cartesian plane plotted with a single triangle, object P. To translate physical mirrors onto a grid, we use the x and y axes as our starting mirror lines. A common mistake is flipping the shape and sticking it directly against the y-axis. You cannot just place the image on the line. You have to measure the exact perpendicular distance from every corner of the object to the axis itself. Because of the equidistant rule, we continue that same measurement directly across the mirror line. If a corner is 3 boxes to the right of the y-axis, its new position must be exactly 3 boxes to the left. This gives us our first mathematical rule. When reflecting over the y-axis, the vertical height stays identical, but the horizontal position changes its sign. Now let's test the inverse logic. Pause the video and look at object P. If we use the horizontal x-axis as our mirror line instead, what are the new coordinates? The object drops directly below the mirror line. The horizontal position stays exactly the same, but the height flips its sign. For standard reflections, you never change the numbers. You simply flip the positive or negative sign depending on which axis access the mirror. This grid shows the diagonal mirror line y equals x. Notice that this is not the x-axis. It is a unique line cutting through the origin, where every coordinate matches perfectly, like 1, 1, 2, 2, and 3, 3. If you draw a shape on tracing paper and fold it along this specific diagonal, you can see exactly where the object lands on the other side. The visual result gives us our third rule. Reflecting an object across the line y equals x completely swaps the x and y coordinates. The final and most complex axis is y equals negative x, which slopes downward from left to right. Reflecting over this line requires a dual action. You swap the coordinates and you flip both of their signs. Unlike standard axes, reflecting across diagonal lines fully swaps the horizontal and vertical properties of geometry. Let's apply these rules to a practical scenario. Imagine a surveyor mapping land coordinates in Jinja to plan a symmetrical city development across a roadway. On this grid map, the surveyor plots a triangular plot, PQR. To plan a symmetrical garden, they reflect the land across the y-axis, changing the x signs for new coordinates. To map a parking lot south, we apply the x-axis rule, flipping the y signs. This summary table displays the precise rules for calculating reflection across the Cartesian plane. Take a screenshot for your notes. Whether plotting a city map, programming a video game, or tailoring a dress, mastering these rules gives you the tools to control the mathematics of balance.